Hey all, Shemai Pow. This is Idna, and today I'm going to walk you through a HackTheBox Sherlock called WorkFromHome. This is a medium difficulty Sherlock from Chicken 0248, and we're given a KAPE triage output and need to answer a load of questions around how the compromise took place. Let's get cracking. So here I am on HackTheBox Labs. I'm just going to browse to Sherlocks, start to look for work from home, and we can just read through the scenario. Wowzer Enterprise or Wowzer Inc. has hired you to investigate an incident involving a workstation used by Othello John, which is believed to have been compromised by a threat actor. The attacker reportedly changed the desktop wallpaper to a questionable image. The IT team has already provided you with initial information, and it's your duty to report back your findings. So I'm just going to download the artifact. So I'm going to copy that to my clipboard so that I can then download that in my machine here. So this is Flare VM. Just got some additional forensic tools added to it. So I'm going to copy that URL into here and wait for that to download. Once we've got that, I'm going to extract that into a directory called WorkFromHome, and the password is can be got by copy to the clipboard by clicking this button here. The password for Sherlock is always HackTheBlue, which you can see by doing that. Okay, so we have now got our initial output. So we can see that this looks to be like a KAPE triage output. That's pretty standard thing. So basically, KAPE is a tool that can be used to you can run it against a machine, and it will extract various artifacts. Depends on the profile that you tell it to collect. So this is probably using something like the SANS triage image, which will go and collect key forensic information from a disk and then present it back here. We've also got this initial information text. I'm just going to open that up and we can read through it. This is the initial information provided by the Wowzer IT team. All internal websites, including login page, are using SSO with Active Directory. All users must access the workstation locally only. Only a single user is assigned to this workstation, which is Othello John. All workstations can be accessed via RDP, and in case of work from home, but no one is allowed to do that yet. Sometimes when IT staff try to receive information about the system via systeminfo, it crashes. Windows Defender was disabled, but then it was re-enabled to try to collect evidences, and that triggered some responses to quarantine a file labeled as Interpreter. And Othello reported that his desktop wallpaper was changed after he logged in on the 28th of May 2025. Not entirely sure what to make of all that at this point, but I think we can basically assume that Othello John is the only user on this workstation. So if there are other logins present, that's suspicious. Inbound RDP connections are suspicious because that is enabled but not in use yet. The incident happened on or around the 28th of May 2025. And that link to SSO, that could indicate that credentials being used in other applications or email and things like that are also likely to be Active Directory credentials. I also want to have a look at some of the information inside this image just to give me an idea of what kind of logging we've got enabled. So if I come into C Windows 32 Win Event and Logs, these are all of the log files that are captured. Many of these are just enabled by default in Windows. Lots and lots of different event logs are in here. I am looking to see whether we have got sysmon. We can see we've got PowerShell, so that's probably going to be interesting later on. Nice to see. Have we got sysmon? We have not. So unfortunately, we don't have sysmon logs. Sysmon is a great tool that gives you lots of information around sort of process execution, network connections, file creations, things like that. Really, really useful from a forensic point of view, also from a detections point of view. But we don't have that here, so we're going to need to work around that. I am going to start off by, we're going to be using a lot of the Eric Zimmerman toolkit in this, so easy tools. Instead of processing each of the, using the easy tools to convert all of the artifacts we've got present individually, we're going to use a KAPE module. So I mentioned earlier on that KAPE can be used for collecting information, but it can also be used for processing forensic information. So we're going to demonstrate that here now. So GKAPE is the GUI version of KAPE. Wait for that to load. Okay, just maximize that a little bit. So we've got the two sort of sections here. Target options, these are what I was mentioning just now, where you can say what kind of artifacts you want to collect from a machine. That's not what we're going to use here. But just as an example, a very common collections of profile, I suppose, these are all things that can point to certain things to be collected. The SANS triage is a very commonly used collection module there. But we don't want to do that. We want to use these modules. The source is what we're going to be asking it to process. So that is our extracted C drive here. So that's the source. Destination, we're going to create a new destination. Let's create it in the same folder though. Where is my downloads folder? There it is. And I'm going to make a new folder in here, just call it output. That's going to put the output of this into that. Where's it gone? We don't need it to flush. That's if you wanted to overwrite things in that directory. It's a brand new directory. We don't need that. But these are the various things we can get it to do here. So there's lots of things you can do. So, extract information like Bitcoin information, things like that. It'll look through the whole thing, looking for various artifacts. We want to use this EZ-Parser. So what that will do, will just go through all of the forensic information there and extract out CSV formatted, I'm going to choose CSV formatted information that can be used then with Eric Zimmerman's Timeline Explorer. It just batches up all of the typical processing you might do. So you might want to normally extract MFT. You might want to extract the Windows event logs, all the various things like that. This will do that for you all in one batch. It's a really, really good little tool. So we've got everything set to go there now. And I'm going to click execute, which you can't see is behind my head. And I'm just going to wait for that to run. It does take a little minute to go through everything, so I'm just going to pause the video and I'll come back when that's complete. Okay, so that has completed now. So I'm just going to click the any key to exit. And we can also close KAPE now. So if I show you what that generated, in our output folder that we created, we have now got, if we look in event logs, we've got a CSV, a 45 meg CSV, which is all of the event logs in that triage output in one CSV. File and folder access information. So things in there around what files and folders were executed, what sort of link files have we got that we can backtrack and see what things were opened. We've got things from the file system record, so master file table. We've got the USNJournal. All this kind of thing going on, program execution, so we can see things around sort of prefetch and stuff like that was coming through. So it's just done all that in one. It's really good. So we'll be using a lot of this shortly. But to start with, I'm going to just look at question 1 to guys where we're going to get started. Identify the phishing URL that the user clicked on, resulting in credential harvesting. So we want to look for what URLs were being accessed here. A good place to start with that is by looking at the browser history. So I've got DB browser for SQLite here. Chromium type browsers store history and other information in a SQLite database. That is an artifact that does get collected by this particular, well, it is in this triage output anyway, so it's collected by the sans triage. We can browse to that. Oh, no, not in there. It's in the raw output. It's in the user's profile. So IntelliJ is our user, IntelliJohn. App data. I'm going to switch that to all, so we can see all of the files here. I will never for the life of me remember whether it's in roaming or local. It is not in roaming. It must be in local. We're looking for the Chrome history. And they might be using Edge, in which case you'd look inside a different folder. But this is what we're looking at here. So this is the Chrome history for that user. This has extracted a bunch of tables. And we can then browse through that information. So 2 of the key points that we want to look at here will be downloads and URLs. So we can start at URLs. And these are the URLs that were accessed. We can see them browsing to wowserinc.co.th and logging in. And we know that those are SSO credentials that they're logging in via. So that'll be their Active Directory credentials. Browsing the internet, looking at their email. And you can see an email here titled Meeting Reminder. So we can expand that a little. So it looks like a meeting invite being created there from within the email. Some Google searching going on, so looking for YouTube, browsing some YouTube feed videos here. More and more YouTube. And we go back to email. You can see this important update email come in. Straight after that, we see login.wowser, and that's an LNC. So that is basically a domain spoofing type attack. It looks quite similar to the original. So if we go, you can see here, wowserinc.co.th, wowserlnc.co.th. So it's made to look very much like it. It's a social engineering phishing email. So that's very likely what's happened here. So they've clicked login on this suspicious URL, a little bit more YouTube, and then some browsing to free hacking tools. So that's looking like this is going to be our area for concentration here. So let's have a quick look in downloads and see what else was going on. We've got 3 downloads here. If I just expand this to the right here, 3 different downloads. We can see we've got something coming down from SE manage volume exploit.exe. We've got a DLL coming down and a VBS or VBScript. We can see where they've come from. So all 3 of these were downloaded from that free hacking tool URL. So if we go back to our URLs, let's just recap on that. So what appears to have happened, this looks to be a phishing email, an important update that's linked through to this domain spoofing. And then at some point, then the attacker is likely to be using the same browser to download some additional tools. Our question is asking us for this URL. So let's copy that. And we've got our first question. when did the threat actor gain access to the victim's computer via RDP for the first time? So we're going to start looking into our logs now. So let's open up Timeline Viewer. Have I got? I thought I put a shortcut in here. Obviously not. In our Easy Tools suite, because we did all of that processing earlier on, we can just jump straight into Timeline Explorer and just load artifacts straight into this and get a view of what's going on. We are going to load in all of the event logs from this host, but we're going to concentrate on successful authentications. Downloads, work from home. It's in the output because this is the processing, event logs, CSV. We want to know when the threat actor gained access for the first time via RDP. So very common thing to look for successful logons is the ID event ID 4624. That is in the security log. If I just clear this for a second, you can see we've got all of the event logs here. So the application logs, various sort of more sort of focused, specialized context logging going on here. But we've got our key players like system, security, and application. But they're all in one, which makes it really handy. So we can just search for 4624. That is a successful logon event, and we can see we've got over 600 of these, 615 to be exact. So we want to filter this down a little bit more. If we scroll over slightly, we can see the URL that was sorry, not the URL, the username that was being logged onto, and we've got this logon type. So logon types, if I just have a look for this, just look at the Microsoft website here for a bit of reference. Each different type of logon has a type, as we would expect. So this table here gives you a summary of these. Interactive logon, so that's basically where you are actually hands-on keyboard logging on. That will give you a logon type of 2. Network logon, so these are things like some examples here. So if you're using NetUse, so you're mapping a drive from another computer, so there's an inbound network connection to that host, or remote registry calls, or things like that, that will be a logon type 3. Batch, service, things like this. Remote interactive is the things that we are interested here. That is specifically about remote desktop. So inbound remote desktop connections will log this logon type 10. Often with RDP connections, you will also see a logon type 3 because there is an inbound network connection happening at the same time. But the actual RDP session will log this logon type 10. So if we come back to here, we want to put a filter in for logon type 10. So I'm just going to type 10 here. And we can now see we've only got 2 of these, both from the user we are interested in. The question is asking us when they logged on for the first time. We can also see some of this is where they were logged in from. So that's the attacker's IP address. But the time we are interested in here is this time created. We don't need to worry about any sort of time zone conversions. Timeline Viewer will extract this in the UTC timestamp, which is what we're going to be wanting for this question. So the first logon was at the 27th of May, 11:59. And there's our second question. The threat actor accessed several sensitive files on the victim's work-related folder. What is the full path of the PowerPoint presentation opened by the attacker? for this, we want to stay in timeline viewer. However, we want to look at a different artifact. So when you open up various documents and things like that on your computer, they will store as recently accessed links, shortcuts. So that then when you can see, often you'll open your start menu and there will be a documents folder, and it'll show you all the documents you opened very recently. I would show you an example here, but I don't have any documents open on this VM. These are stored, they're in the registry, which is why they're in the registry folder here. And they're recent docs, is what they're known as in this kind of forensic artifact way. So we can see we're going to look at the recent docs for the user that we're interested in. And here we can see all of the recent documents that are opened here. So we're looking for a PowerPoint file. So the extension for PowerPoint is PPT or PPTX. Is PPTX we've got here. So we can see proposal to CFO is the file name that was opened. However, we're looking for the full path. You can see this full path is actually, that's the path to the recent docs shortcut, not where that file is actually stored. So we want to find where that file was on the disk in order to be able to answer this question. For that, we want to look at our master file table. So again, in our pre-processed CSVs here, we want to look at the file system. And we've got MFT, which is our master file table. That's just a large database of every file and folder on the file system and lots of metadata around them, such as when they were created, the size, the location on disk, when they were last modified, all this very information. So it's a forensic treasure trove. We're looking for proposal to CFO. So we can start to type that in here. Proposal to CFO. We've got, it's not the LNK files we're looking for, that's the actual shortcuts that we were just mentioning in recent docs. It's the PPTX. This is a temp file, so this is the actual one we're interested in. So the full path is C users, IntelliJ, desktop, working, proposal to CFO. So if I just open that up, start to copy that into my clipboard, and we'll fill that in on our question. And we've got our question 3. The threat actor discovered a privilege that allows specific volume level management operations that could be exploited to get full control over the C drive. What is this special privilege? So we already know that the attacker, if we go back to our browsing history here, they downloaded a tool called SE manage volume exploit.exe. So this, we can look for this and see what we can find, and we find this GitHub repo. This explains that so this exploit grants full permission on C drive for all users of the machine, and it's exploiting some local privileges, overwriting printconfig.dll. So we saw printconfig.dll also get downloaded, and this is exploiting a particular privilege here, and it's this privilege we want to find. So it's the SE manage. It's related to the privileges to that, but we want to find the actual name of it. This tweet here, being linked in the exploit, I mean, this is documented in other places as well, but this is a nice place where it shows it. This is the actual name of that privilege that is being exploited in that in the exploit we just saw. So that's the sort of the actual name that we're looking for here. And that is our question 4. What is the name of the executable downloaded by the threat actor to exploit previously found privilege? So that is the exploit we were just referring to. So that's this one here. We saw them downloading this in the browser history. So we can copy that. And we've got question 5. What is the full URL from where the threat actor tried to download a DLL file? Again, this is in our downloads in the browser history. So the DLL was downloaded here. Well, it was attempted to be downloaded. I'll come on to that in a second. We can see there's actually 0 received bytes, but we will talk about that shortly. But this is where it was coming from. So we can copy that in, and that is not right. I wonder if it wants the name of the actual file as well. I guess that's the full URL then, I suppose. Yes. Okay. And as we saw, that was the same DLL that was being referred to in the POC. Number 7, the malicious DLL file was not successfully downloaded as the download was interrupted by the safe browsing safety feature. Research some browser forensics and find a description of the interrupt reason that caused the download to be disrupted. So coming back over here to our browser histories, we can see, like I just mentioned, let me just scroll that over a second. For this particular file, it's 9216 in total, 0 received bytes, state 2, danger type 7, interrupt reason 41. So we want to do a bit of research and find out what these mean. Specifically, the question is asking us what description is associated with that interrupt reason. We can do Chrome browser forensics. Let's start the search with DFIR actually. Oh, sorry, shortcuts everywhere. DFIR Chrome browser forensics interrupt reason. Probably isn't going to find exactly what we want. Okay, so there's the AI result. That's not getting us exactly what we need here. We can start to look around. The DFIR blog is a good tool. That's not the exact link we're looking for, but yeah, research these sorts of things, and you'll be able to find the answer somewhere. But I've got a link here that gives us a really nice explanation of what is actually happening from the DFIR blog. So they got a screenshot here of exactly what we were seeing, really. And they have just summarized the various things that we were seeing. So in refresh our memories here, so we saw the state 2, danger type 7, interrupt reason 41. Danger type 7, dangerous host. So safe browsing, download service, check the contents of the download. Didn't have data on that file, but the file was served from a host known to serve mostly malicious content. So basically it didn't like the website it came from, even though it doesn't understand the file. We saw interrupt reason 41. and that's actually browser shutdown. It's looking for the description. So in the table here, we can see value, name, description. I would have expected this really to be 7, but possibly Smart Screen does something that logs it somewhere else, it gets classified as a browser shutdown. I'm not entirely sure, but either way, what we actually see here, interrupt reason 41, is a browser shutdown, and specifically the question is looking for that description. So that is what we are going to enter here. Number 8, since the download was not successful from the browser directly, which lolbin did the threat actor use to download this file successfully? A lolbin is living off the LAN binary. A common one attackers use is Certutil, but we don't want to assume that was used here. We should try and find evidence of this. What we can do is, if we have a look at when this was attempted to be downloaded, so this timestamp here, so this is a Chrome WebKit timestamp, so we want to convert that. It's a little bit like epoch time, although it actually isn't epoch time, but it's like it in that it's a number of seconds since a particular date. Chrome timestamp converter, that will do. This is what we want, WebKit timestamp converter. Yes, I consent. Okay, so we can copy in what we found here, and the download was attempted on the 28th of May, 12:44:01. So that is what we heard in that initial information around when the activity was happening that the user spotted. But what that does, that gives us a start point to have a look at when things were happening in the files being downloaded and created. So in our MFT, again, this is the master file table. We want to look for files that were created around about that time. So I'm going to look for things created greater than, let's give it 28th of May 2025. Let's actually expand that filter a little bit and put a time in there too. So to do that, we can enter T. What was the time we were looking for? 12:44. Let's just do it from 12:44. Let's see what files are created after that time. We want to make sure we're sorting by the same field, so we are seeing things in order. All right. Here's our file names. It's the time they were created. Let's just scroll this over a second and we can see some more things going on. So I said that Certutil is a common tool that attackers use to download files from the internet. Certutil stores metadata about files downloaded and the actual file downloaded in these in the user's profile, in the local profile in this cryptnet URL cache. You can see there's 2 entries for this here. So it's typical that you would have 2 file names the same. One is the metadata about the download, one is the actual content. And they were created shortly after that time. So the browser blocked the original download, so the attacker's gone to a different way, sort of just under a minute later. So we want to have a look at those files. In our triage output, let's go to It's in downloads, work from home. So it was in the user's local profile, local low, Microsoft, cryptnet URL cache. There's those two folders. The file name we're interested in, let's look in content. Okay, there doesn't look to be anything in content with a timestamp that we're interested in. We're looking at the 28th of May. These are all the 23rd. Let's just confirm in our MFT. So that file ends in BBB6. And there is nothing with that in our content folder. So that file isn't part of the collection for some reason, or it was deleted or something like that. You can have a look at our metadata. And here we do see that information. I just sorted that again by time. 1245, BBB6, that's the one we're interested in. I'm going to open this in a hex editor, so HXD, just because it's easier to view what's going on here. And we can see that this is where it came from. So HTTP free hacking tool tools, and then the file is printconfig.dll. So this pretty much confirms that Certutil was used to download that file. So we can enter that as our answer here. Actually, before I do that, I'm just going to quickly look at the other files that were downloaded around about the same time. We can also see free hacking tool tzres.dll. So we don't know what that is yet, but the attacker also downloaded that around the same time. We'll be coming back to that. But to answer this question, which lolbin does the threat actor use? It wants a file name .extension, so that is certutil.exe. There we go. Question 9. When was the malicious DLL successfully downloaded using this lolbin? So that we can see in the MFT. So we know that it was downloaded here. This is the file creation time. So that should be our answer for this. And it is. Question 10. To gain system privileges, the threat actor replaced an existing DLL with the same name. What is the original path of the legitimate DLL? If we think back to the POC for this exploit, this lists the original file of printconfig.dll as this drive here. It's likely to be the same on ours, but let's find it. Excuse me. So yes, let's find that locally and find some evidence that that is the case. For this, we will want to use the USNJournal. So that's this $J. And let's look for files with that name. So the USNJournal is basically as the name might suggest, it's a journal of what happens to each file. So if we use this as an example, we can see file creation, data extended, rename, delete, overwrite, things that will happen to that file name. This is, okay, so we've got these parent entry numbers referred to the location of that file, which is what we're looking for here. We need to cross-reference these with the MFT to find out what those locations are. We've got the two here. So first one is 11794. So let's look in MFT. We need to get rid of our filter there. Look for the parent entry number field. 111794, 111794, and that is the user's download folder. Fine, that's what we'd expect. So the first time we see that record of that file being created is in the download folder. Next thing we see happening is in 4245. So let's look at 4245. And that is Windows System 32 spool drivers x64.3, which, if we come back here, is the same path that the POC mentions. So that's some reasonable confirmation of what's going on there. If we follow this journal through, we're basically seeing the file being downloaded and data added to it, which is part of the download. The original one being deleted. And then basically this is then being copied from here to here. So that's basically the overwrite process happening. So yep, we can pretty much confirm that this was the original. This is the legitimate path for that DLL, where the malicious one was overwritten. Oh, sorry. And then the file name is printconfig.dll. Great. Question 11. The threat actor removed the illegitimate DLL before replacing it with the malicious DLL. When was the legit DLL deleted? So that is what we just spoke about in the journal. It's deleted here and then the new one written in its place. So that delete happened in this entry here. And that occurred at 12:47:06. When was the malicious DLL detected as malware? Back in our event logs, we will have some defender logs here. You can see a bunch of defender logs here. It's event log. I'm just going to clear that a second. Event log 1116 is what we are looking for. That is a malware alert, malware detected event. So if we use these, let me just add that filter to clear out the ones that have got unrelated logs there. Great. Okay, so we've got these 4 entries. I'm going to scroll these over. And yeah, so you can see 1116 is detection event. Interpreter detections, that was mentioned in the initial info. Detection times. And here's the actual executable that it picked it up from. So that's the print config. So we can see specifically it's the print notify within that DLL that it doesn't like. The 4 entries all to do with print config. We are looking for when was it detected as malware. So that will likely be the first of these entries. And the first is 319. Yep. The threat actor initiated a Windows component to load this DLL. What is the class ID of this component? Again, if we refer back to the POC, these are the commands to basically run that exploit, and it's calling this class ID here. We will likely want to try and find that being run here to evidence that that is how the attacker performed that exploit. there's a few ways we could potentially find this. We've got PowerShell logs, so we could look around for that. There's a lot of logs here. We've got 1,600. PowerShell logging is pretty noisy. But it is also very, very useful, of course. So we can have a look through, see, it'll be probably in one of these payload informations. We might be able to find it. Payload data 1. The command tends to sometimes get spread across these fields, so we may not find it this way. Nothing in there. Actually, does it say the string CLSID? Yes, it does. Okay, we got something in the script block. Okay, let's just open that. All right, okay, that's it. That's exactly what we see in here. So that is basically confirming the class ID. That's the same one we have in the POC. There's actually another artifact we can use to see this. Because the attacker was logged in via RDP, they were using the GUI sort of things, and we've got the PowerShell CLI GUI, if that makes sense. And commands entered into that console are logged in the PS read line. So if we look at the user's profile, I believe that's roaming. Yes, so PS read line. So this file here will contain the commands entered into that console. So we can see they entered dir, they ran the command we just saw in the script block log. They also then finished off the second line of that. So that's this one here. I think object activated create instance type. Yep. So this is the commands exactly from the POC. They then added registry entry, the desktop wallpaper. We know the wallpaper was changed. This is the path to that. We'll come back to that as we progress the investigation. At the moment, this is the information we need. So we can see that logged in two different places, the PowerShell script block logging and also the PS read line because it was entered into the console. So let's just copy the class ID being used here. And we've got our answer there. What is the name of the service or object associated with that class ID? We could see that being called in the script block. Oh no, sorry, it was in the detection. So if I go back to the detection, 1116. We can see the service is being called from that DLL here as print notify. It is also mentioned in the POC, so, initiating the print notify object. So that is pretty comfortable to be our answer for this. So I'm just going to copy that from there. You can likely also just search for that class ID on the internet and find out what is associated with it. What is the SHA-1 hash of the malicious DLL file? If we had sysmon logs, we would likely be able to get that from this, and it logs process executions and the hashes of those files associated with the process. We don't have sysmon logs, so we might need to find this in another way. One way is Defender logs diagnostic type logging locally, certainly where it's enabled to do that. And that is in this C Windows Defender support in this log here. So if we open this up, all sorts of diagnostic logging going on here. It's very useful to understand if maybe the antivirus is taking up additional resources or is hanging on a particular when trying to scan a particular file. This is the kind of log that's really useful for that. In this case, we're going to use it for another reason. So we're going to look for, let me remember what is the SHA-1 hash of the malicious DLL. If we search for that DLL in here, we have this entry. So this is basically querying the Defender sort of cloud repository of information. What is the reputation for this file? We've got two hashes here. We've got the SHA-256 and the SHA-1. SHA-1 is what we're being asked for. And that is what we will enter when we can finally move the screen. A second DLL was downloaded from the same malicious domain. Where was it downloaded on the file system? Now, remembering back to our Certutil, we saw, if we just open that back up again, or do I still have it open in the hex editor? I do not. So let's go back there. So it was C users, a tel of J, app data, local low, Microsoft, cryptnet URL cache, metadata. So we saw this was the extra DLL that was downloaded, tzres.dll, and that has got this file name. So let's just copy that, and then we can look in our MFT, our master file table, for that entry and find out where it was saved. We know it was saved here. Of course it was saved here. That's the Certutil. Oh, sorry, that's what I'm looking for. Yeah, so this is the it's 9216 and it was saved at 12:54:22. If we search for that file, tzres.dll, we see the only one is got the same sort of time, 9216 in size, 12:54:23, so 1 second later. That is effectively the same file. We pretty much can confirm that. And that is stored in this file here, this folder, I'm sorry. Just to sort of go over that slightly again, how I made that association. We know the file is called tzres.dll. We're looking for, we know that was downloaded at 12:54:22, and it was 9216 in our master file table. 1 second later, there's a file of the same size with the same name that's been put into this location. We can also probably look in the journal for this. Yeah. Yeah, again, I think we've got the original file being created and overridden going on here. Okay. When was this DLL downloaded on the system? So once again, we want to look for not necessarily this file creation, but the one we had just now, which was this file here. Nope, not that one. That one there. I'm sorry. Oh, I'm in the journal, that's why I'm getting more entries. Yes, right, now finally. So that was downloaded at 12:54:22. Okay, so this is where some confusion is. So the DLL was being downloaded at 12:54:22, but it got the final location 12:54:23, and I think that's what's being got at here. So it was downloaded to the target destination. Then Certutil has a local copy that was saved 1 second before. A little bit confusing there. Sorry about that. Question 18. The threat actor downloaded a VBScript for command execution to facilitate the DLL execution of the second malicious DLL. What is the full path of this script after it was moved to a new location? We going right the way back to here where we saw this VBScript being downloaded. We know it's called a.vbs. So once more, we want to look in our master file table to find out where a.vbs was moved to. So this is the sort of the current location of that. So it was in the downloads folder originally, and then it's been moved to the startup folder. And this also got a zone identifier showing it was downloaded from the internet. We should be able to see, yeah, so we can see here that was downloaded from that page, even though it has ended up in the startup folder. Once more, I'm assuming we'll be able to see this move happening in the journal. So it was downloaded to the downloads folder. That was that 111794. So this is the downloads folder. 1456 will very likely be the entry we're looking at here. 1456, yes. So it's been copied from one to the other. Copied or moved. It'll be moved because the original one isn't in the master file table. Okay, so the question, the full path after it was moved to a new location. So that's this startup. So that's going to run that VBScript anytime anyone logs into that computer. So basically it's like a persistence type mechanism. And then the actual file was a VBS. Cool. Number 19. What is the full command that the script is configured to execute? Because of the location that is in, we will have a copy of this in our triage. So what was the location? See program data, Microsoft Windows start menu. See program data, Microsoft Windows start menu, programs startup, and here's the VBScript. So let's open that up with Notepad++, and we can see it's basically this is VBScript for running this command here. So this is running systeminfo. So that's the command that it's running. So that's the answer here. And we will come on to why that is running systeminfo right now. Number 20, the threat actor configured the VBScript to be hidden from the Windows GUI. When was this attribute set on the file? Back in our journal, if we remember, the journal is where changes to files are recorded. We've still got a.vbs filtered here, which is what we want. We just scroll over to our attributes, and we can see that the hidden attribute was added in this entry here. So let's just highlight that row so I don't lose it. And that happened at 12:56:11. Task 21. Which process loads the previously identified DLL with this command? The command executed by the VBScript ultimately facilitates loading and execution of the second malicious DLL, providing persistence and execution capabilities to the attacker. So we know so far that the attacker placed tzres.dll in Windows System 32 WBEM. So if we just scroll back up, we can see that here. We know that the attacker placed that file, the file that they control, in this folder. We also know that they've created a VBScript in the startup which runs and calls systeminfo. What this is asking is to connect those two dots. The privilege escalation vector going on here is documented online in quite a few places. The best place I could find to really demo this is in the write-up. Sorry, I'm just going to copy this into my path here. The write-up for this shows this example here. There's lots of places you can find this information out, but I think this one tweet really showcases what's going on here. So this is a good example of how to demonstrate what's happening. So this is, you can see the process map here. So in this command window, systeminfo is being run. When monitoring what happens on the system, then WMI PRVSE.exe is trying to load tzres.dll, but that is not found. So that file does not exist. What this tweet is saying, if you control that tzres.dll, you can write to that, WMI PRVSE will load it when you run systeminfo. You control that DLL, you control the commands that are being executed inside it, and you can use that, you can make that do whatever commands you want at your leisure. So in this case, they've got a reverse shell running, and they've used it to exploit privileges and escalate to system. That is what's going on here. So fundamentally, the information we want to answer this question is, actually, if we just find the question again, what process loads the DLL with that command? So what process loads the malicious DLL when you run the systeminfo command? As demonstrated here, that is WMI PRVSE.exe. I would encourage you to do some research on this to find out more detailed documentation of what's happening. I'm using that tweet as a way to quickly highlight what's happening, but there's a bunch of research on it. It's really interesting. I'm going to have a look at that. Number 22, the threat actor downloaded an image file to change the desktop wallpaper. What is the full path of this file? If you remember back when we were looking at the commands run in PowerShell in our PS read line, you can see that this is the file being set as the wallpaper. So that is the answer we want here. Looking at that, actually, they are not Windows. I mean, you enter that into PowerShell, it will still understand it, but that's more likely. That's a Windows formatted file path rather. But yes, PowerShell is intelligent enough that if you did enter it like that, it would recognize it. Number 23, the threat actor then proceeded to change the desktop wallpaper of the compromised user to the newly downloaded image. Find the time when the wallpaper was altered. So basically we're looking for when did they run that command. Again, if we had sysmon here, we'd be able to see when that registry key was changed. We don't have that. What we do have though is the PowerShell logs of when that will have happened. So let's go back to our event logs here. We can clear out 1116. That's not what we're after. Let's look in the provider for anything containing PowerShell. And okay, we've got the filter going on for that here. So now if we look in our payload data 2 was the script block. So maybe we can find it here. Yes. So as before, we could see things being entered into the console also being logged in the script block text. So that's the command we just saw. Yep. PS readline doesn't log timestamps. Script block logging does. So this is the same command. We want to know when that happened. So scrolling across to the timestamp here, that was changed at 12:59 and 30 seconds on the 28th. When did the victim user log into their workstation after the compromise? Okay, so back to the original thing really then. So still in our event logs, we want to look at 4624 events again. This time though, we know the user logs in locally. And if you remember back in where we were looking at the logon types, a local logon is a logon type of 2. So we can once more filter for logon type 2. The user is Otello J. So let's, and these are all the logon type 2 for Otello. Let's look at our timestamps. All of these happened before the incident. This is the one that happened after the incident. And then finally, what is the message on the new wallpaper? Okay, so the wallpaper was stored at C users public pictures. We can check our collection, C users public, but the pictures folder is not here. We can look to see if this is in our MFT as a resident file. So resident files are basically MFT will store a copy of a file if it's under 1024 bytes, and they are known as resident files. So you can actually view files from within the MFT. If we look for gg.bmp, here is the MFT entry, but that file is too big. We can see here that this file was created at 12:58:24. If we just put in a filter here for, let's do the same. So 2025, May, 28th of May, 12:58:24. What's going on here? 12:58:24 I said, wasn't it? Okay, so let's do that. That should give us anything created around that time. But we'll remove the GG. We just want to look at all files created at that point. this is what I wanted to highlight here. So at the same time as the gg.bmp, we've got a file of this exact same size created in the cryptnet URL cache again. So that is once again indicating that Certutil was being used to download that wallpaper. As we know, Certutil stores the content as well as metadata about where it came from. In the past, we haven't had a copy of that, but let's have a look if we've got this one. This time it's in the system profile. So that's the system user's profile. That's because the privilege escalation was already run. That SE managed volume exploit was run and they got system access. Actually, no, it was the systeminfo tzres dll exploit that got them system access. So we can look in this file here. Actually, let's look at the metadata file and find out what this file is, first of all, and where it came from. So in Windows System, System32, config, system profile, app data, and then the cryptnet URL cache. The name is this one that ends in 22dba. 22dba. This is the metadata, so let's view that in a hex editor. freehackingtool.com gg.bmp. So this is what we are interested in. Let's look at content, and we've actually got that this time, so 22 dba. If we want to confirm that that is the actual file, we can look at the magic bytes. So if we open this in the hex editor, you can use online to find out what these magic bytes are. They're the file identifiers. Here I've got detected easy installed, which is a method of quickly identifying this. So I can open that in detected easy, and that is telling me that this is a Windows bitmap. At least according to the magic bytes, it's a Windows bitmap. And that is what we're interested in. So I want to open this in Paint. And here we can see that's what the wallpaper was changed to. Hacked by Anarchy is the message. So if we come back over to our flag, what is the message on the new wallpaper? Hacked by Anarchy. There you go. That is work from home. So that wraps up work from home. Thank you for watching. If you like this, please do like and subscribe to the channel. If you manage to solve any of the part of that Sherlock in a different or better way, please do leave a comment. I really want to hear more about that kind of thing. Please check out Sherlock's on HackTheBox. We release a new one every single week. There are over 100 to play. Many of them are free. For now, diolch yn fawr.